Hello, I'm Dr. Jacob Hudis. In this presentation, I'll guide you through solving 4 essential problems on inductors and self-inductance, helping you build a solid understanding of these fundamental concepts.
Because solving problems is the only way to really learn physics.
Problem 1, titled Inductor Showdown. The figure below shows 2 inductors connected to voltage sources. 1. Determine which inductor carries a larger current. 2. Identify which inductor exhibits a faster rate of change of current. 3. Determine whether the current is increasing, decreasing, or remains constant.
Party!
And here's the answer to problem 1A. There are 2 inductors, and we're given that one inductor is 2 henries and has a back EMF of 2 volts. There's also a 1 henry inductor with 4 volts of back EMF. And we're asked to determine which inductor carries the larger current. Faraday's law tells us that the magnitude of the back EMF over the inductor is equal to L di dt. If the current changes through the inductor, there will be a back EMF which works to oppose that change. Since the magnitude of the voltage is equal to L di dt, the current I cannot be directly determined from the information provided. The back EMF is only related to the change in current. It has nothing to do with the magnitude of the current.
Terrific!
If you had an inductor which had 1,000,000 amps of current going through it, that'd be pretty impressive. That doesn't tell you anything about the back EMF over that inductor. That only tells you how much total current is going through there and how strong the magnetic field is. The back EMF is related to how that current is changing. Problem 1, part B asks to identify which inductor exhibits a faster rate of change in current. I know the magnitude of the back EMF of an inductor is equal to L di dt. I can solve for di dt by dividing both sides of this equation by L. This tells us di dt is equal to the change in voltage over L. For the right inductor, the change in voltage was given to be 4 volts, and it's a 1 henry inductor, so that tells us that the current is changing at a rate of 4 amps per second. Same calculation for the left inductor gives us the current is changing at a rate of 1 amp per second. And finally, part C says, determine whether the current is increasing, decreasing, or remaining constant. Well, we know it's not remaining constant because there's a voltage over the inductor. And if the current were constant, there'd be no voltage over the inductor. The current is decreasing in both inductors because in both cases, the polarity of the EMF is the same, and therefore the current is decreasing. Problem 2, Solenoid Secrets. A solenoid inductor generates an electromotive force of 0.2 volts when the rate of change of current through it is 10 amps per second. At a constant current of 0.1 amps, it produces a magnetic flux of 5 microwebers per turn. And the question wants us to determine the number of turns in the solenoid. Faraday's law tells us that the magnitude of the voltage across an inductor is equal to L di dt. We can take this equation and solve for L, the inductance of this inductor. When there's 0.2 volts across the inductor, the current is changing at a rate of 10 amps per second, and that tells us that this is a 20 millihenry inductor. We want to find N, the total number of turns of this inductor. The flux through any inductor is related to the current in the inductor by the proportionality constant L, where L is the inductance. It's related to the geometry. A given current for a given inductor produces a given flux. Phi1 is the flux through one turn of the inductor. N times Phi1 is the flux through the total inductor. This is proportional to the current flowing through the inductor. The proportionality constant is L, and this L is the inductance. It's related to the geometry of the setup. I can solve this equation for N. N equals Li over the flux through one loop. We know L, we know the current, and the flux through one loop was given to be 5 microhenries, and that tells us that this is a 400 loop inductor. AcePhysics.org. Math and Physics Tutoring with Dr. Hudis. Problem 3. The graph below shows the current through a 10 millihenry inductor over a time interval of 6 milliseconds. Draw a graph showing the potential difference across the inductor during this time interval. We're given a graph of the current going through an inductor, and as you can see, the current is changing with time, and we want to plot the voltage across the inductor.
Let's do this!
We know the voltage across an inductor is equal to negative L di dt. We're not taking the magnitude, so the negative sign is important. In segment 1, the current goes from 0 amps to 2 amps in a time interval of 2 milliseconds. So di dt is 2 minus 0 divided by 2 milliseconds, and that's 1,000 amps per second. EMF is equal to negative L di dt. L was given. That's negative 10 volts. In segment 2, the current is decreasing. It goes from 2 amps to negative 2 amps in 2 milliseconds. So di dt is negative 2,000 amps per second. The EMF across the inductor is positive 20 volts. And we draw positive 20 volts here. And I'll let you work out segment 3 on your own.
The final example problem is number 4.
An electric generator contains a coil with 120 turns and a diameter of 18 centimeters. The coil rotates at a frequency of 60 Hz in a constant magnetic field, oriented perpendicular to its axis of rotation. Calculate the magnetic field strength required to produce a maximum voltage of 170 volts.
A generator converts mechanical energy into electrical energy through the principle of electromagnetic induction. When a rotor, the rotating component of the generator, spins within a magnetic field, it causes a change in magnetic flux, inducing an electromotive force. This process produces alternating current. This is an example of a generator. While it may look large and complex, its core function is straightforward. The rotor spins within a magnetic field to generate electricity. This fundamental process underpins all generators, including the one powering the lights you're using right now.
And here's the solution to problem number 4. The flux through one turn is equal to the area of the coil times the magnetic field times cosine of omega t. Faraday's law tells us that the EMF is equal to negative the time derivative of the flux. The derivative of cosine of omega t is omega sine of omega t. To get the EMF through the entire coil, we multiply by n. The maximum EMF occurs when sine of omega t is equal to 1. Here we have a formula to solve for the maximum EMF when sine of omega t is equal to 1. This equation allows us to easily solve for B, the magnetic field, and when we plug in all the values, we find that the magnetic field is 0.15 Tesla. AcePhysics.org, Math and Physics Tutoring with Dr. Hudis.